everyone. Welcome to Eyes on Earth, a podcast of the U.S. Geological Survey's Earth Resources Observation and Science Center. I'm your host, John Holt. On today's podcast extra, we'll hear from a handful of the EROS staff members and graduate students who took part in our fall poster session. A poster session is essentially a way for scientists to share their work with their colleagues in a public forum. The posters in the atrium for our session covered a variety of topics on remote sensing, satellite technology, and geography. I pulled aside a few of the authors during their hour-long site visit to hear more about their work. First up, we'll hear from a South Dakota State University graduate student who used land cover maps built with satellite data to investigate switchgrass as a more sustainable alternative to corn in ethanol production.
All right, so we're here with Logan Meagard. He's got a poster. It says, "The Potential Area of Switchgrass for Biofuel Production in South Dakota." Right?
Yes.
Okay. So what problem are you looking at here, Logan?
So I'm looking at renewable energy source that can replace corn. What I'm looking at specifically is switchgrass, which can be grown on marginal land and has less inputs than corn currently has.
Less inputs, you mean cheaper to grow?
Less fertilizers, less irrigation, so it can be more sustainable.
So what did you do to sort of figure out how much area is available? What are we looking at here?
I used two data sources, the GAP land fire cover data from 2011 and then land cover national land covers from 2016.
And since people aren't going to be able to see this, we're looking at a geospatial data set. We're essentially looking at a map that tells us what parts of the land are forest, developed, cropland, etc. So that's what you're talking about. You're trying to find areas that are not currently used for crops that could be suitable for this switchgrass, right?
Yes, I'm finding areas that aren't currently used for cropland or developed or water, cut out forest as well, because we don't want to cut those down.
What did you find?
Between the two data sources, I found 3 million hectares and 2.1 million hectares that are in this usable area.
In those two data sets, you found 3 million in one and 2.1 million in the other.
Yes. For those 2 to 3 million acres, I found that you could produce 5.37 to 7.67 billion liters of biofuel a year.
So there's a significant possibility there. There's a significant opportunity that you
Yes. The only problem with it is that it's more renewable, but it's also not profitable, which is why it hasn't taken off yet.
The National Land Cover Database that Logan used for his study is produced at EROS. Logan used land cover data, but the database has several components. One of them defines how much grass and shrubland covers each 30 by 30 meter plot of ground in the western United States. Let's visit with one of the EROS contractors behind that project.
We're here with Matthew Riggy, and he has a poster that says, "Validating a Landsat time series of fractional component cover across western U.S. rangelands." What on earth does that mean?
It means that we're just trying to figure out a way to validate our fractional maps, so 0 to 100% cover maps.
So fractional is 1 to 100%.
Exactly.
Okay.
Yep. Across a big time and space. And these maps span from 84 to 2018. So since we don't have a time machine, we're trying to figure out a way to use existing data sets to validate previous years where we can't go out and collect field data anymore.
And by validate, you mean make sure that you're right, essentially?
Correct.
Check your work?
Not even to make sure that we're right, to quantify accuracy. Let's put it that way. So we're looking in Nevada, Wyoming, and Montana. We had a series of high-res satellite images, so like 2-meter satellite imagery and field data collected at the same time and same place.
Gotcha. When you talk about field observations, you have someone on the ground saying, yes, this is sagebrush, this is cheatgrass, whatever it is that you're looking for.
Correct. And not only that, but like what is the cover of each of those from 0 to 100%? What's the cover of those?
Okay, so we know, because we were on the ground, we know this is 80% cover, and then you get your 30-meter data.
Correct.
And it says whatever it says.
Right, and then compare those two.
Compare the two.
Yep.
Gotcha. And you're talking about an accuracy assessment for a mapping product, essentially,
Correct.
right? This is an NLCD product?
Well, it's like a subset of NLCD.
A subset of the National Land Cover Database.
Yep.
I see. And why does this matter? Why would you go to all this trouble?
It's important because we want users who would be like land managers, for instance, to have confidence in our products, to know that they can reliably use these data to answer the science questions that they have.
The Landsat data used for land cover mapping will soon be available in the cloud. Let's hear from one of the EROS contractors working to make cloud-friendly Landsat a reality.
All right, so we're here with Renee Pischke. Did I say that right, Renee? Okay. And your poster is Landsat in the cloud. Can you tell us what you were looking at here, what you were studying, what this is about?
So the Landsat Product Improvements Project has been working on putting Landsat into the cloud for the past 2 years. We're getting closer. We've got 6.5 petabytes in the cloud right now. Collection 2 will be processed in the cloud. So this poster is focused on how end users are going to access the data and a little bit about the new cloud format, the cloud optimized GeoTIFF, and this new metadata format called the spatiotemporal asset catalog, which is pointing directly to cloud assets as they are sitting in their cloud locations.
This is a spatiotemporal asset catalog. This is a stack, right? Now, this is a tool? Is that right?
This is just a format of metadata that will allow you to access the data programmatically. So if you're in a Jupyter notebook, you can query Landsat data where it lives. You don't have to download any of the data at all.
And you say how soon is it that people will be able to use this?
We're looking at Collection 2 release in the spring.
Remote sensing scientists spend a lot of their time working to fine-tune satellite data to make it more useful to those who need it on the ground. Let's hear from an EROS contractor who recently published a paper that explains how to improve the resolution of daily satellite readings over active fires.
Okay, so we are here with Sanath Kumar, and his poster is titled An Algorithm to Downscale MODIS Satellite 1 Kilometer Daytime Active Fire Detections. Now, I'm guessing that some of our listeners might not understand what that means. Can you tell us what you're doing here, what you're looking at, what problem you're trying to solve?
Well, we're looking at fires in space, and there's an inherent problem. The thermal sensors we have, they're about a 1 kilometer resolution. So basically what it means is, if we say a fire happens somewhere on a location on Earth, we don't know where within the first 1 kilometer radius it's there in, right? If we can reduce that uncertainty, that'll be good. That'll be good for fire managers. We know where the fire is. So this work kind of reduces the uncertainty. And hopefully going forward, we can possibly do it to the nearest 30 meters to 10 meters.
Great. Well, how'd you do that? How did you approach this problem?
Physics, the Planck's function, actually, it all comes to fundamental science, right? I mean, how radiation is, at what wavelengths, depends on the temperature and the area, and what spectral wavelengths are of interest. For example, if you heat a rod of iron, first goes red, right? And then it goes blue hot or white hot. So by just looking at the color temperature, you know how hot it is, right? So by measuring the intensity of how much blue or how much red it is, we also know the size.
Okay.
So by using thermal sensors, we can actually have an idea about what's the size of a fire and what's the temperature of the fire. So the big takeaway is, yes, the technology is improving and we can go finer and a higher temporal resolution. So it's like having more precise data, right? Excellent. Previously we had an approximate data. Now we're zoning in onto the more finer details.
Now who's going to use this, or maybe who is using this method now?
Well, as of now, it's a recent publication. Nobody's using it right now, except me. But hopefully the fire managers, for example, the California fire that happened, if we know the location of the fire, it'll be useful for people, the first responders. It'll be useful for the management crew. So these are the immediate people who might find it of interest. The secondary interest is for people who are monitoring the science aspect of it, how the fire spreads and grows. So in a 1 kilometer fire, we can't see the growth of the fire unless we map it for multiple days. Whereas if you have a higher resolution product, we can see how the fire, the direction which it's moving. So we can relate it more to the ground. Right. So we can have a better fire spread model. So that means we can understand the effects of fire, how it grows in the landscape, and it can help in future fires how accurately we can predict. So
excellent.
It has good repercussions, yes.
Wonderful.
Thanks for listening to Eyes on Earth. We hope you join us for the next episode, which you can find by visiting usgs.gov/EROS. This podcast is a production of the U.S. Geological Survey, Department of Interior.